All right, here we go. We are recording. So today I'm going to talk about designing PCR primers. I guess this would be like an interactive lab. And I'm just going to walk through the process of what I would do to physically design the PCR primer so you guys now get a good sense of how to do that. A first thing I would draw out is I do want to answer this question of how are PCR primers different from cloning primers? Okay, so if you haven't gathered, you can do many different things with PCR. If I typically say like run a PCR reaction, usually what's happening is somebody is checking something for like a plus versus a minus status. Like, is something there? Is the symbiont there? Can you detect it? Has a serial killer been here? Can you detect his DNA? That's kind of like a PCR, a standard like PCR test. The primers for that are going to be different from PCR cloning primers. Okay. So in this case, where you're just checking, is something there, you're going to design basic primers that essentially look like this. Okay. And we'll walk through what that means. But they're just kind of like normal primers. They're essentially like about 26 base pairs long. And that's it. They match the sequence. That's it. Now, in cloning, it's different. Okay. In cloning the primers, the PCR primers, the goal of cloning is you have a destination plasmid. And in cloning, your goal is to PCR an amplicon and to insert that amplicon, maybe gene X, into your plasmid. So the goal of cloning is to capture something and then place it somewhere. Whereas the goal of just a standard PCR is to just check, is something there or not? So there's two sort of like different goals, and the primers are going to be different in a sense that to do like the paste functionality, you have to start building stuff into your primer. So you have to add a couple extra things onto your primers that aren't necessarily just the sequence of your target amplicon. So some of the things that we're going to be adding today are going to be restriction enzyme sites. Okay. And then after the restriction enzyme sites, you typically put a few random sequences, and I'll explain why that is. So essentially the gist of this first question is, how are PCR primers different from cloning primers? PCR primers are just kind of like standard boilerplate. Cloning primers have extra stuff added on, usually on the ends. Okay. Everybody should understand that. If you don't, ask a question. Okay, so step one, pick. Okay, so here's what we're gonna do. We're gonna design primers to clone gene X. That's what we're gonna do. Okay, so step one, pick your destination plasmid. Okay. Today, I think we're gonna clone a yeast gene. So we're gonna clone some yeast gene X into a yeast plasmid. Let's pick PS2. PS2 is 2 micron. So is that high copy or low copy for yeast? Write it in the chat. Yep, very good. It's a high copy plasmid. So that 2 micron is the origin. It's about 60 copies per yeast cell. And PS2 is a Ura3 cassette. So this is auxotrophic selection, not bacterial selection. Okay, it's different. If you aren't familiar with this, you should have watched the yeast lecture. So it's a Ura3 cassette, which means that in order to select for it, we would leave uracil out of the media. That's how we would select for it. Okay, so it's got Ura3 cassette selection. And it's going to have a Gal1 promoter. I might as well just draw it. It's going to look like this. PS2, Ura3 selection cassette, 2 micron origin, a promoter with Gal1. Gal1 can be turned on with galactose and off with glucose. Okay. And then there's going to be MCS upstream of the promoter, which is a multi-cloning site. And that multi-cloning site is going to have various restriction enzymes. So pick our destination plasmid, PS2. Right now, I'm actually going to pull up the PS2 manual. PS2. Actually, I'm just going to pull up plasmid map, add gene. Nope, this is not it. I clicked the wrong one. Here it is. Add gene PS2. Here it is. Here's the map. Hang on. How can I? There we go. This is the map. Let's confirm my drawing. 2 micron origin. Here's the Ura 3 cassette. It's got an ampicillin cassette. Why would it have an ampicillin cassette if it's a yeast plasmid? In the chat, answer. Why does it have an ampicillin cassette if it's a yeast plasmid? If it's a yeast plasmid, why does it have an ampicillin cassette? What is ampicillin? What is ampicillin? Answer in the chat, or I'm going to make everybody turn on their microphones. Yeah, it's essentially like this plasmid. It's designed for, the purpose of it is yeast expression, but you build it in E. coli. So the reason it has an AMP cassette, ampicillin is an antibiotic. The reason it has an AMP cassette is because you can build it in E. coli and you would select it with ampicillin antibiotics. If this language that I'm using like is not making sense, you are like way behind. Okay. So this should be fast. You need to study a lot more if this language is not making sense. Hopefully you understand. We should all be able to like read these maps now. So it's got an ampicillin cassette because it's an antibiotic resistance cassette for bacteria, so you can build it in bacteria. PBR 322 origin. So you'll notice it's got 2 origins. It's got the 2 micron origin. That's the yeast origin. And it's also got a bacterial origin, so you can replicate it in E. coli. Here's the multi-cloning site. These are all restriction enzymes. Okay. This is the terminator. That means this is the promoter, Gal1 promoter. So it's going this way. Now, obviously direction is going to be important here, because if we clone it backwards like that, if we clone whatever we're going to clone in there backwards, that's going to be a huge problem. We need to orient the gene in the direction of the promoter. Okay. So these maps are super important. So picking your destination plasmid, the next thing you need to do, step 2, is get a map of that plasmid, and you need to have it like ready to consult. Okay, so we got that. Okay, step 3, find our gene of interest on NCBI. Let's go to NCBI. Let's clone a yeast gene. So I'm going to search for a gene. Let's clone SRP1. It's a gene. It's a name. Carioferin. It's a carioferin. Carioferin alpha from yeast, which is Saccharomyces cerevisiae. Yeah, it's got a weird spelling. Hopefully I spell it right. Let's see if we can find it. Here it is. We found it. SRP1, carioferin alpha, Saccharomyces cerevisiae, S288C. It's a standard like line. It's on chromosome 14. Let's click on that sequence. Let's pull the sequence. Here's the gene. Very interesting. The gene has a single exon. That's convenient. It's not complicated. Okay. let's get the FASTA record, which is going to pull up the gene for me. Here's the gene. I'm going to take this. I'm going to put it in Sublime. I'm going to remove the spaces. So I'm going to search for the new lines. I'm going to replace them with nothing. I'm going to copy this. Now I'm going to put it in Word. Oh, did that not work? Somebody have a question? Somebody like unmuting their microphone? There we go.
So what did you just put it in to remove all the spaces?
Did you watch the lab video?
No.
Okay, I refuse to answer that question until you watch the lab video. Watch the lab video. I explain it there. Okay. It's essentially, okay, I won't be mean. It's essentially a text editor, and it helps me remove spaces. I discussed it in the bioinformatics lecture. Make sure you check that out. It's very useful, as you just saw. I'm teasing you. Okay, so we got our gene. Now, sometimes I like to have some different options, okay? I might want to clone the promoter and the terminator. We have to decide like what part of this gene we're going to take, okay? So let's also pull 500 base pairs upstream. So that means we would subtract 500, which is going to make this 3760. And let's add 500 base pairs at the end. If you kind of like add 500 base pairs, you're probably likely to get the promoter and the terminator. So let's add 500 base pairs to this end. So it'd be 8, 9, 10, which would make this 6, 3, 8, 8. Now we're going to update. Now this is that same sequence with 500 base pairs upstream and downstream. So let's take this. Let's pop that in Sublime. Control H. I'm finding the new lines to get rid of them. I'm replacing them with nothing. Replacing them. I'm just copying now and pasting it into Word. Okay. Now the next thing I'll do is there's a useful font in Word. So let's switch the font to Courier New, and let's make it small so we can work with it. The nice thing about Courier New is the Courier New font has the exact same space for every single letter. So it lines up perfectly. The other fonts won't do that. So every time I'm working with DNA or protein, I always switch to the Courier New font, because now everything is perfectly aligned, exact same amount of space for every character. Okay, so now here's the start codon. Here's the stop codon. Now this section is the same stuff, but with plus minus 500 base pairs. So let's find the start codon in the thing at the bottom. So I'm going to control, find. Here's the start codon. Let's find the stop codon. Here's the stop codon. So in theory, the promoter's up here. In theory, the terminator's down here. You might not know for sure, but like I said, if you get 500 base pairs, you'll probably grab it. So now we have two options. Okay, if I want to clone this gene, I could either design a primer right here and right here, which is going to essentially clone the ORF. So I need to decide, step 4, decide if I am cloning the ORF or promoter plus ORF plus terminator. Like I need to make a conscious decision. And it's going to depend on the plasmid. Okay, let's look at the plasmid map, where it's going. this plasmid, does it already come with an inducible promoter? Does it already have a promoter? Yes or no in the chat. Does the plasmid PS2 already have a promoter? Yes, it does. Okay. So in this case, it doesn't make sense for me to clone out the endogenous SRP1 promoter and pop it into this plasmid, which already has a promoter. That makes no sense. Okay. I would use a different plasmid for that. This promoter is designed for galactose-induced expression. So the only way that this is going to work properly is if I directly clone from the start codon without taking the promoter. Does that make sense? So I'm not gonna use this, but I showed you how to pull it out in case you ever want to do that. So I'm going to design my PCR primers literally at the start codon. So whatever I pop in is right there in front of that promoter, the GAL1 promoter. Okay. So let's pick some primers. Okay. What's the rule? What base should my promoter or my primer end with? What base should it end with? An A, a T, or a C, or a G? Write it in the chat. Yes, thank you. We need to follow the CG clamp rule, okay? So G's and C's have 3 hydrogen bonds. They're tighter. I want the end of my primer on the right side in this case. Just so you know, the direction of this DNA is 5 to 3. I want this end to end on a C or a G, okay? And the primer would actually be better if I didn't start with this A. So if I look down here, like the nearest C that I could start with on the left side is here. That's too far away. I don't want all this extra crap. So if I was to follow the CG clamp rule on the left of my primer, I'm going to be adding in all this extra crap. I don't really want that. It wouldn't cause a problem in this case, but there are situations where it could cause a problem if you're adding in extra stuff in front of your gene in between a promoter. In this case, it wouldn't matter because eukaryotes are pretty lenient on space between promoter and start codon. If it was a bacterial expression plasmid, it would matter a lot. Okay, so I'm just going to start at this A. Okay, let's try ending on this C. So let's test this for primer. How do I test it? What are the things I want to know about it? Okay, the first thing I want to know is annealing temperature. So let's take this, copy it. Let's pull up a program called OligoCalc. OligoCalc is going to calculate properties of oligonucleotides. Okay, I use this all the time. So you just paste your theoretical primer sequence here and you hit calculate. And here's what you're looking at is the salt adjusted annealing temperature, the melting temperature. And the reason it's salt adjusted is because our buffers that we're running PCRs in are going to have a little bit of salt. So this is the one we want to look at. So it says 57.6. That's pretty good. Okay. So this looks, at this point, it looks like a good primer. Let's check the self-complementarity. So what that's doing is if you check self-complementarity, you have a primer. It's checking if you flip that primer, could it bind to itself? Could it bind to itself anywhere? That could cause problems. So let's click check self-complementarity. It's going to check for hairpins, which are things that look like this. And it found none. And it found no potential self-annealing sites. So this is a perfect primer, beautiful primer. Okay, so let's mark this. This is going to be our forward primer. Now, anytime you make a primer, you need to properly annotate it. So let's call this primer JFB 001 forward. This is the 5' end. And now the sequence. Okay. And when you use molecular biology, you will develop a list of many, 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 many primers. So they all need to be properly annotated. It's extremely important. Okay, and let's annotate a couple other things. Let's annotate that this was 57.6 degrees Celsius annealing. That's going to be important. Okay, now let's look for a reverse primer. So if we want the full gene, the reverse primer is going to have to start somewhere on the end. Do we want a stop codon or not? Should we include the stop codon in our primer? Yes or no? Write it in the chat. Somebody other than Kylie, write it in the chat. Yes, very good, Andy. We do want a stop codon, okay? We need a stop codon because if I was to clone in my gene X without a stop codon, okay, it's going to synthesize a transcript that's much longer, and the ribosome is going to read this, and it's going to make my protein, but it's also going to make a bunch of extra crap at the end, okay? And that's going to alter the protein. So I need to include the stop codon. So the end of my primer must be at that stop codon or after it. I cannot end the primer before, okay? So I'm going to start here and work my way in. This time I want the CG clamp on the left, okay? The left side. And the rationale here for that is, how do you know where you want the CG clamp? Well, I know my RNA or my DNA polymerase in my PCR reaction is going to be moving this way. So this needs to be tight, okay? And on this side, it's going to be moving this way on the other strand. So this side would need to be tight, okay? So I need a CG clamp on the left here. So let's extend these in. Let's make a guess. Let's try this. Here, I'll end with a C. Let's copy this. OligoCalc. Let's test this out. Calculate 51. That's too short. That's much too short. It's not high enough, okay? PCR, you want 56 to 60 degrees Celsius. My other one is 57. I want something that matches right around 57. So I need to add more base pairs. Okay, this is trial and error. So let's add in these extra 3 so that we end with the C. Let's try this. Calculate 55. I could go a little bit further if I wanted, although it's starting to get good. Let's see what happens when we go to this GT. GT. Let's try this. $59. That's better. I'd rather have it hotter on the hotter side because it's more specific. Low temperature primers are sloppy and they'll bind to anything. Okay. I would much prefer a hot temperature annealing. So this looks pretty good. Let's check the self-complementarity. Maybe. Something has happened. I've killed the pop-up. Let's try it. There we go. Awesome. It checked for hairpins. There were none, and there were no self-annealing sites. Let me show you what it would look like if there was a giant hairpin. We can write in a giant hairpin. A. T. This should form a giant hairpin. Let's check it. Boom. Anytime you see something like this, this is a red flag. Your primer sucks. It's not going to work. Destroy it. Think of something different. Change the base pairs. Pick a different spot. If it ever looks like this, your reaction is bound to fail. Okay? So you have to walk through your primers, look through each of these things, make sure it's going to work before you buy them. But we know our primer is not like that. Our primer is like this. Beautiful. Okay. So this is good. This sequence is good, but we're not done. Okay, this is not a reverse primer. If I was to just take this direct sequence running 5 to 3, this is not a reverse primer. It would be another forward primer. Okay, what I need is a reverse primer going the other way. So to get that, I need to take this sequence. Remember, we need to generate a primer that's moving this way, the other direction of the DNA. So I need to take this, copy that. I need to go to Google, and I need to go to reverse complement. Use this website all the time. Very, very simple, okay? Paste in my sequence. Now this can change. You can either take the reverse, which is just gonna take the exact sequence and flip it, or you could take the complement, which is gonna give me the matching strand of DNA, or you can take the double, which is the reverse complement. That's the one we need. Okay, for a reverse primer, you need the reverse complement. So let's take the reverse complement, submit it. The algorithm takes the reverse complement function, copy that. Now this is the sequence of my reverse primer. And actually it's in 5' to 3'. This is how you have to order it. Whenever you order primers, they must be written in 5 to 3. So what we just did is translate to a reverse complement primer that we can buy that will work in our PCR reaction. And we can check it, okay? If it's correct, this G is essentially matching this C. This T is matching this A. This C is matching this G. You see, it's the reverse complement. If you don't understand that, I got nothing for you. It takes a while to get fluent with this, but you won't get fluent unless you just do it. Okay, and let's remember our annealing temperature, 59.2 Celsius annealing. Okay, so we have literally just designed PCR primers. This would work in a standard PCR reaction. If we were just to take these primers and we could extract DNA from the yeast and we could run a PCR reaction and it would amplify this product. The size of the product, let's annotate that. The size of the product is review, word count, 1,629 characters. That's 1,629 base pair size amplicon. That's a good thing to annotate in your primers because whenever we PCR this, we're going to want to sanity check it for size and compare it in an agarose gel to a ladder. So if it matches at about 1,629 base pairs, we're good to go. If it's something else, it didn't work. Okay. But we're not done, okay? Because what we really want to do is we want to clone SRP1, just the ORF, into PS2. We're not just PCRing, we're cloning. So these primers are not done yet, okay? So how are we going to get it into the plasmid? Now's when the restriction enzymes come in, okay? And we should know what restriction enzymes are. Restriction enzymes find palindromes. So imagine CG, CT, wait, I'm trying to remember, GGATCC, GGATCC. I think this is BAM-H1. And if you read this way, it's the same as reading the complement the other way. That's called a palindrome. Restriction enzymes find these sites and they cut the DNA like this so that it generates these overhangs that match. And BAM-H1 might actually cut like this. It might actually be like that. I can't remember. Okay. This is just an example. So what this would generate is it would generate sticky ends of DNA that combine each other and match. This is how we stick things in cloning. Okay, so the next step is step 6. We need to decide what restriction enzymes to use for cloning. Okay, and we need 2. We need 2 so that we can direct the direction of the insert. So if you only use 1 restriction enzyme, say your restriction enzyme is A, what you're doing is you're creating an insert that has A on the left and A on the right, and your plasmid has A on the left and A on the right. And this could insert like that, or it could also flip and insert backwards. Okay, so if you just use 1 restriction enzyme or blunt end cloning, there's no control of the direction of the DNA. If you use 2 restriction enzymes, A and B, and you make your insert A and B, it's only got one way that it can stick in. Okay, because the B's overhang only matches the B and the A's overhang only matches the A. So we want to do that. That's usually the best way to do it. Restriction enzymes are cheap. Like there's no reason you can't do 2. It's just a pain in the butt to use 1. There's weird situations where that might be optimal that you might want to do that, but most of the time, 90% of the time, I'm cloning with 2 restriction enzymes. So how do we know which ones to choose? Let's look at our map. These are our options. This is the multi-cloning site, okay? And we have to follow the direction. The promoter is an arrow. It's going this way. It's following this way. So our start codon needs to be one of these restriction enzymes, and the other end needs to be one of these. So let's try BAMH1. BAMH1 is my favorite because it's super cheap. So let's try putting, we got to try this out. Try 5' BAMH1. And let's use one of these at the end. Zhou1 is also one of my favorites. Super cheap, and it'll be good. So if we put Zhou1 on 3', then what we're doing is we're creating a construct that looks like this. BAMH1 on the left, Zhou1 on the right, or 5 to 3. This is what it would look like. So this would be our start codon, ATG, stop codon, TAG. Let's try this. Okay. In order to try this, we need to know the restriction sites for BAMH1 and Zhou1. Okay. So let's go to NEB, BAMH1 cut site. NEB is New England Biolabs. It's where you buy your restriction enzymes. Here's BAMH1. I think it's GGATCC. GGATCC. I was right. Here's where it cuts. Okay. GGATCC. So BAMH1, let's document this. BAMH1 is GGATCC. Let's get Zhou1. Zhou1, I think, is CTCGAG. Let's test my memory. Zhou1. For goodness sake. Hang on, let me go to Google. Zhou1. CTCGAG. Damn, I'm good. Oh, I take pride in knowing random crap. Okay, let's see. So these are the sites that we could use to clone this gene in with sticky ends. Now, we can't do this if any of these sites are inside of the gene, okay? Because these sites are going to dictate where the enzyme is going to cut. So if any one of these sites is inside in the middle of our gene, it's going to cut our insert. It's going to cut our insert in half. Imagine there's a B site inside and at the end. It's going to cut our insert into two pieces, and our cloning is not going to succeed. So we need to check to see if the restriction sites are in our putative insert. So now we need to control find GGATCC. And the only one that it's finding is where I typed it here. So that one's good. This one's a go. Let's check Jo1. CTCGAG. That one is also a go. This one is good. Now, if you did not remove the spaces, there's a scenario where if you didn't remove the spaces, and if you were looking at a document where there was a new line inserted, so if there was, say, I can just write it actually. If there was a sequence that looked like this, CTCG, new line, AG. So if we didn't remove those spaces, it's not going to find that. Okay. And I've made that mistake before of you ruin a clone because you didn't find an internal restriction enzyme site because you did not remove those lines. But if you remove them, it'll find it. Okay. But these enzymes are good to go. So now all we literally need to do is add these onto the ends of our primers. Okay. GG, AT, CC. That one's going to be on our forward primer because remember we want it on the left. And this one, we can also literally just type it on the left side of this 5', CT, CG, AG. The reason you can do that is because it's a palindrome. So really what we're doing is if you would go back to that primer and type CT, CG, AG here, this is really where you're adding it. And if we were to take this and take the reverse complement, it will be the same thing because it's a palindrome. Oh, my pop-up. Yep, there it is. CT, CG, AG, TT. See, that's exactly what I just typed. So it's actually really, really easy to add restriction enzyme sites to your primers. You literally just pick your primer, and then you literally, once you have your primer organized from 5' to 3', you literally just type in the restriction site on the end, on the left side of the primer, okay? Now, we're not done. These primers will not work. And the reason they will not work is because when you have a restriction sites on the ends of your amplicon, okay, so if this was our SRP1 gene, we amplified it, and on this side, A is equal to BAMH1 and B is equal to Jo1, this would not be able to cut. And the reason it can't cut is because when you get the A enzyme and it tries to come in here and cut it, it has nothing to grab onto. There's nothing for it to hold on to, okay? And same thing with the B. There's nothing for it to come in here and hold on to. So in order to cut, to actually produce cuts, you have to add in some extra sequence at the end of the primers, okay? So 4 base pairs is enough. So let's just put AAAA. AAAA. This would be enough to get a good efficient cut, okay? And you don't have to worry about this because you're literally cutting this off of your amplicon. So this will get loaded into your amplicon. Your amplicon will have AAAA after a PCR, but as soon as you clone it and cut it, it'll get cut out. So we cut this out later. That's why you don't have to worry about it. So these primers, they should be ready to go, but you need a final check, okay? What I usually do is we've added now a bunch of extra sequence on this primer. It's entirely possible now that we've created a primer that is now messed up. So let's recheck it in the oligocalc. I repop it in. The annealing temperature will change, but I don't worry about that because this is not what's annealing, okay? This is what's annealing, and that hasn't changed. So the temperature, the annealing temperature we want has not changed, okay? But the self-complementarity might have changed. Yep, so now we have added in a hairpin. So GGATCC, that added in a hairpin. At this point, you have two options, okay? One option is, so options, if you generate a hairpin. The best option, if you're really being rigorous and you can make it work, pick a different restriction enzyme, okay? I could literally just pick a different restriction enzyme. We've got multiple options in our plasmid backbone. I could try XBA1, I could try NOT1, I could try EcoR1, although here's one of the issues that you're going to encounter. Don't ever try to clone something in between two restriction enzymes that are immediately proximal to each other. So remember, we have BAMH1 on the left. Don't ever put yourself into a situation where you're picking the one right next to it, because oftentimes what's happening is sometimes these restriction sites even overlap. So you could have a restriction site where this is BAMH1 and this is Echo R1, and they might overlap. And so if you try to clone with this on the left and this on the right, you just messed it up. There's oftentimes not enough space in between proximal restriction sites to clone. So a good rule of thumb, never pick two restriction sites that are immediately next to each other. Okay, so if I was being rigorous, my one option is to pick a different restriction enzyme, and then I would pop a different one in and check it. Okay, option two is, if you're good at PCR and you're confident, if you are good, run a hot start. That will get rid of the hairpin and just clone that way. Usually, because now I'm lazy and because I'm good, I'll usually just like run a hot start, as long as the hairpins aren't like outrageous. Like this is only one hairpin. I know I can get rid of that with a hot start just based off experience. I wouldn't worry about it. If you're trying to clone something and you want to succeed for the first time, pick a different restriction enzyme, okay? Or use a hot start. Let's check our second primer. This is what I want. Oh, these pop-ups. I gotta like close them every time. There we go. Same thing happened here, but this time the hairpin was induced by the random base pairs that I added. I can change that. These random base pairs aren't an issue. I can change this. Let's just make this CCCC. Let's see if that makes it better. The random bases at the end, it doesn't matter what it is. You could pick anything. Oh, that pop-up. That fixed it. So all I needed to do was change these four bases. That fixed it. So this is the only one with a hairpin. Let's mark it. Has a hairpin. So that means on these, I need to run a hot start. These are important things to notate. Okay. Now I could make this work. Okay. We've now successfully designed primers that are going to work to clone SRP1 into PS2. Let's just finish the annotation. So usually when I'm annotating primers, I give them a name. I denote which primer it is, forward or reverse. I denote the 5' end. I give the sequence. Usually if I pick a restriction enzyme, I will underline the restriction enzyme or have it bold so I know what it is. And then I'll actually write it in. So this one has a hairpin and it also has BAMH1, and it's BAMH1 on the 5' end. And this one has Jo1. Actually, let's leave this off here because it's going to make things complicated. But I'll note that the reverse has Jo1. Okay. Now I usually will write like a little sentence that tells me like the purpose of the primers. Okay. So I will write, these are primers to clone SRP1. Now you need to note where you're getting your genomic template from. So I would say from yeast genomic DNA into PS2 with an amplicon of 1,629 base pairs, and on the 5' end will be BAM-H1, and on the 3' end will be ZHO1. That's a good annotation. And then now what I do is I literally just collect a Word file that has database all these primers, tells you exactly what they do, tells you exactly what I designed them for. And when you get to the point where you have 1,000 primers, this becomes essential. Okay. That's it. That's how you design PCR primers. So if I wanted to clone a gene, this is the good way to do it. If I wanted to PCR, I would just need to run these sequences without those restriction sites. That would work for a PCR. That's it. Any questions? So you should be now at the point where you watch the PCR up to the why use topo. I never use topo. People use it because it's fast. So topoisomer, I think, I don't actually know if it's topoisomerase or what. I don't know what the actual enzyme is, but it's called the topo cloning kit. And it's a blunt end cloning kit. It's where you essentially like PCR an amplicon and you blunt end clone, stick this into here, stick this into here. The gist is it can clone forward and backwards. The gist of why you would use it is, again, what's your purpose? Most people who clone with topo, they're just looking to get a quick sequence. They're going to run like a Sanger sequencing reaction, or they're just capturing some DNA to subclone it later. So if you're not worried about like building like the final construct, topo can be a real fast way to clone out a gene. But it's kind of like if your step of process is step 1, clone with topo into like a gateway plasmid, and then step 2, clone out of topo into like an expression plasmid. Like you could, some people will do this, but then I kind of think like, well, why even do that? Like, why not just start at step 2 and just always clone with restriction enzymes? Restriction enzymes can be expensive if you're using like weird ones. That could be an issue. Another thing with topo is I believe it's not sequence dependent. So it could be a problem if you are trying to clone your gene into a very specific plasmid and you're limited in the amount of restriction enzymes that you can use. You might not be able to find a match that works, that you might have long internal sites. So there are reasons under which like you might use topo, but I frankly never use it. I just don't do it. Other labs have different philosophies and they have different ways of doing things and they have different purposes at the end. Most of what I do is I'm cloning a lot of expression constructs. So I'm usually just popping it in the direction that I want it, right into the plasma that I want it. That's my gist. Does that kind of make sense? It's good to get experience with both ways. Okay, let's end there. That's 50 minutes. Catch up on the lectures if you haven't seen them. You all should be very, very familiar with PCR. The next module is now like methods of like manipulating DNA. So this is now a good segue into restriction enzyme cloning, which would be the next lecture to watch. And then we segue into genetic modifications like site-directed mutagenesis, modifying plasmids, adding tags, inserting stuff, deleting stuff, things like that. Things are going to get more complicated. So make sure you really understand what has happened here. Okay, have a good day.